So welcome to the third and final video in this series on the binomial expansion. And what we're going to do in this video is take a quick look at some other kind of problem solving style examination questions that you might come up against. So here we go, here's our first one. We've got an expansion of 2 plus kx to the power 7 and we're being asked just to write down the first three terms. So we're going to proceed as if we just knew all the numbers, but we've got a k in there as well. So here we go. First term 2 to the power 7, because I know that the binomial coefficient is 1. I know that kx to the power 0 is also 1. There's the three parts of my second term, and there's the three parts of my third term. So we're just going to proceed as normal now. We're going to do the tidying up. 2 to the power 7, 128. In the next term I've got 7 times by 64 times by kx, and the third term I've got 21, which is 72, 32, and again note the careful use of brackets. I've got k squared x squared from multiplying out kx all squared. Tidy that up, and there is my expansion. Hopefully we'll realise that that's fairly simple and straightforward. On to the next part of the question. We're going to be asked to use what we did in part 1, and we're given the fact that the x squared coefficient is 6 times the x coefficient. So we're being told that this value here, 672k squared, is 6 times as big as 448k. So what I'm going to do is just take this statement that we've got here and just write that as an equation. So we know 672k squared, so there's the x squared coefficient, is 6 times the x coefficient. So there's my equation. I've got a quadratic there in terms of k, so I'm going to solve this, and there's a couple of ways of doing it, but what I'm going to do is put it equal to 0, and then I can choose either to factorise or use the formula, and in this case I'm going to factorise. There it is. And so you can see that that leads to a solution where I've got values of k is 0 or k equals 4. Now, in the context of this question, if we had k equals 0, then we wouldn't get an expansion at all. We just have 2 to the power 7. So our solution here is saying that, well, k is not going to be 0, k is going to be 4. Right. On to another type of question. What we've got here again is an expansion. This time we're going to be asked for the first 4 terms. Again, it's a two-part question. We're going to be asked to use what we did in the first part to solve a problem in the second part. So let's just do the first part first. Let's do the expansion. Same as before. First 4 terms this time though. So I've got 1 to the power 6. There's my second term, third term, fourth term. Just notice that the question asks for 4 terms, but that takes us up to the power cubed term, the x to the power 3 term, not the x to the power 4 term, because the first term is obviously this term at the front here that doesn't have a power x. Tidy those up. There's 1 plus 6 times x over 5. This term here, 6c2 is 15, x squared over 5 squared, which is x squared over 25, and the third term, 20x cubed over 125. It does say to give each term in its simplest form, so I've got to do a little bit of tidying up. And there it is. You'll notice that the only tidying up happens in this term here. 15 over 25 is 3/5. 20 over 125 becomes 4 over 25. And there we go. First 4 terms, each term in its simplest form. On we go then to part 2. Now, this might look like a strange question. You might be thinking, you know what, I can just whack that into the calculator, and absolutely yes, you can. But what this is going back to a little bit is this technique, and you'll see this next year, can be used to give approximations for square roots, cube roots, and those kind of things, which was actually a very useful thing to be able to do in the days before we had calculators. So going back to the good old days, our kind of famous mathematicians of the 17th, 18th century would have been using these kind of techniques to help them solve problems involving roots. So that's kind of gives you an idea of why we might want to do something like this. In this particular context, this is more about just checking or testing your understanding and your problem solving skills. If I'm going to use my expansion to solve or get an approximation for 0.975 to the power 6, what I need to do is say, well, if I look at this thing here, that 1 plus x over 5, I need to choose an appropriate value of x such that it becomes that expression 1 plus x over 5 becomes 0.975. So I need that thing there to be the same as that. So I'm going to write down an equation. 1 plus x over 5, I need it to be 0.975. And now I can calculate what value of x is going to make that happen for me. Move the 1 over, multiply by the 5. There we go. I know the value of x I'm going to need is minus 0.125. So what we're going to do is say, well, 0.975 to the power 6 is going to be the same as this thing here, where I've kind of put in my value of x. And all I've got to do now is say, well, this expansion here is going to be the one I've got in blue up here, but just with minus 0.125 replacing the x each time. So whack that in, and now it's just a case of working out the value on our calculator. So grab your calculator and you can make your life a little bit easier just by typing in initially minus 0.125 equals. That will save that value under A and S on your calculator. So when you type into your calculator now, you can just use the A and S key, which just saves you a little bit of button pushing. Put all the numbers in, and we end up with 0.8591. And that's an approximation for our 0.975 to the power 6. And you notice you can always check that you've got these right, because you have got a calculator in the exam, so you can just do 0.975 to the power 6. And as you see, it turns out to be 0.859068301. And so what we've got there is a correct value from our expansion that's correct to 4 decimal places. And if you wanted it more accurate to more decimal places, all you would have to do would be to increase the number of terms from your expansion that you'd use.